Good. Welcome back. I have 7 participants online, so we're a little bit larger group again. So today I was going to give you a survey over approaches to vehicle path planning. So that essentially reviews other approaches, and we'll look in more detail into the potential field approach. So by the nature of that topic, it's a little bit more of a survey. In some sense, I sometimes say, that kind of approach exists without really, so you get more an awareness of the field. I'm not explaining every approach in detail. It's also somewhat boring to do that. I will make available, it's already on the webpage, to the exercise that I uploaded. There is a chapter from the handbook on this topic, which is not a very long chapter. A very good background reading for the lecture as well. And then the exercise invites you to study one particular question that I'll point to here now in the lecture. So please interrupt me. I'm teaching a little bit rapid pace here. There's no real reason for that. So just keep interrupting me. Also online, just speak up. I don't always see the comments. Okay, good. So to remind you of the problem of vehicle path planning is this problem we had this slide before of going somewhere in a 2D world on the surface of some environment and going towards targets, avoiding obstacles. That's typically the sort of thing that we're looking at. There could be sometimes other things. We'll get a few examples where maybe you want to follow a road, a path, for instance. That would be a typical additional kind of constraint that I'm referring to. And I want to briefly review these basic approaches. So very few words about classical planning. Let's see what that means. And then I'll be talking about the potential field approach that is closely linked to the track dynamics approach of this sort of variance of each other. And I'll compare these two. And the exercise actually is for you to study that a little bit at a conceptual level. And then I think the order might not be exactly the right order. I actually added here something where I go a little deeper into the potential field approach to talk about behavior-based robotics. I had mentioned that in the survey, and the potential field approach is very routinely used in this spirit of behavior-based, and I'll expand that a little bit. And then I'll talk about the Borenstein and Coren method that's quite relevant. It also has some relationship, or track dynamics is some kind of extension of that. And the dynamic window approach I'll mention maybe a little bit earlier. And the last is to show you some extensions some of my former students have made on the track dynamics approach. Very cool demos. That's what we do. Actually, I realized that I changed the order without changing the slide, so I'm not going to follow exactly the order. I'm not even sure right now which order I have in the slides. Okay, good. And so classical path planning, there's a lot of information on that. So this was a field that attracted a lot of attention, especially early in autonomous robotics in the 90s, 80s, 90s. But keeps doing that. And that was primarily in this dense plan act picture, where you could have the planning as a separate thing, and the sense would lead to having a world model. And so you would say, given the world model, I can do planning, and it's a separate thing. And you can see that is good for as an academic discipline. You have your own little field. You don't have to take into account all the other things, the control, the sensing, the world modeling. And it's also inviting in a sense of system integration. That is, if you have the architecture algorithms, you can have the planning part, and it doesn't interact too intimately with the other parts, which is hard to maintain as software and so on. So there are a lot of reasons that push people to have these cleanly separated stages and modules of processing. There was a little bit of a disillusion for a while in that there was sophisticated math there. People did what I mentioned earlier, to exact approaches where they could always find a path if there is one, and made all kinds of exotic limit cases that are hard. But then in practice, it couldn't really demonstrate that, because the perception of the robots was so bad that the world models were quite bad, and the things that mattered to the planning didn't really impact on reality. So there was a little bit of a disillusion with that. The approaches I'll mention later, the potential field approach and the behavior-based variants, were in part a reaction to that. They are not exact and they are more local, ad hoc, and so on. And as I mentioned in the introduction, in the meantime, these things have been married a little bit. There's both a deliberate planner that does this sort of stuff, and then there is a more ad hoc reactive planner that's not using these algorithms. So the book chapter I will give you is this Kavraki-Laval. Laval is sort of like a famous name in this field. And Latome is sort of the elder statesman in this field, and he wrote a big textbook. Both the Laval and Latome, these textbooks I said here, actually are available online. I think they have made it available, so it's not even illegal. You can search that. These are relatively thick books. You don't want to read the whole book unless you are really interested in something in there. This review chapter that I cite here gives you a survey and also has the exact references. So in this kind of approach, you have the world model given. It's typically given in terms of some areas in the 2D world that are obstacles or other targets or other kinds of things that you might want to take into account, like if you have VR points or you have streets, things like that, that can also be that plan. And then your goal is to find and you also have a model of the robot. I'll come to that. If the robot is not a point, right, or it might have some shape, and you have to make sure that it doesn't collide with any part of its body. Yeah. And then your task is to find a path that is collision-free from any initial position, very typically any initial position, to the target. And so there's a whole large set of different approaches, which again, I've just mentioned that they exist, some of which are exact mathematically. They can prove under some conditions that defines the paths. One important concept there is the concept of configuration space. That's a concept that also generalizes to planning for arms. So the notion there is that you have a space that describes the possible kinematic states of your robot. So here's a somewhat arbitrary academic example where the robot is a triangle. So it can be described by its position and then the angular orientation of the triangle. This triangle is the robot, right? Which is a funny academic example. Usually you wouldn't build a robot to be a triangle. And it just illustrates that if you have that robot and have a square obstacle, you could then construct a representation of the obstacle in configuration space. That would really just mean that all the body configurations that lead to collision would then be highlighted in that space. So for instance, here, this set here, these two surfaces are the ones when you shift the triangular robot along this line and along that line, these would be all the configurations that would be just at collision. So you would want to stay away from these configurations, and you can see how you could expand that for high dimension spaces. So that's one way of how people do that. That is, they have a world map in lower dimensions, and then they expand it into high dimensions through thoughts like that. Even that itself, mathematically, is not always trivial to do. So the book chapter goes to that. I just want to put, this is like from Laval's more recent edition. It has a name, it's the Piano Movers Problem, just to highlight that you can get pretty sophisticated that way. Let's say you have a world model as indicated here, where there are complex objects in the world. And here's an exercise of having, I think, 4 mobile robots, three mobile robots that support a piano, right? And the way they would have to maneuver to get it through the door, let's say, can be complex even for a human. And then you would want to have a framework where it can do something as complex as that. That can be quite complex. In fact, some of the people who analyze how these algorithms depend on the number of constraints or complexity kind of analysis. How does it scale with the number of constraints and so on? I don't think that there is any real practical case where things like that are done in this shape, but it's sort of the academic discipline that establishes these methods. Again, I'll not explain now how these work, but that's sort of the style of that field. And you can imagine that you can do complex stuff even if the assumptions seem very simple. One of the approaches that is most common is that you have what's called a sampling-based approach. So if you don't, the direct way is really a theoretical thing where if you continuously many configurations or continuous spaces, in those spaces you would have to figure out sets that are that can be entered, and then you have to look at a path continuous through that space. You can see that that's really not doable on a computer. That will be something that you do with proofs or some mathematical formalization. And if you do this numerically, then one notion is to have sampling-based approaches. So essentially, you're generating a graph of configurations such that you find out that you can move from one node on the graph to another without collision. And you essentially try different places like that, and then establish that you can move between those. And so iteratively, if you can, then you remove that point from the graph and so on. So over time, you develop a reduced representation, so that you only have to move within that graph, roughly speaking. There's a lot of more sophistication about that in that field. So the chapter will give you a little bit of a review of that. I didn't really want to say more about that. It's sort of orthogonal to how we do things, and it's its own little literature. Okay. I'll talk much more about the potential field approach. So the potential field approach is already a dynamical systems approach. Mathematically, it's not always formulated that way. In the little chapter I'll give you, it's actually framed as gradient descent, sort of algorithmically, but it's ultimately a dynamic system. It says that you make an update of your state variables. It's often thought of like stepwise, like an Euler discrete approximation of dynamic system. But it says, given my current state and given some kind of forces, abstract forces, what's my next step? So that's in some sense a dynamic system approach. In some variants are explicitly dynamic systems. And so this approach was developed in the 80s. Mr. Makati actually working then in Toulouse. He's now a famous professor at Stanford, just beautiful work. He was the inventor, someone called Neville Hogan, who is now at the MIT. I think he was always at the MIT. Developed something that's related called impedance control, or impedance approach or something. And I'll not talk about that here, even though that's interesting to us in controlling arms. Just historically, sort of similar ideas arriving at about the same time. Khatib's approach has been used a lot for vehicles, even though he developed it initially primarily for robot arms. I'll not really go deep into that here. The same approach can be used in these two ways. And the notion is that you are erecting a potential field. So potential field is just a scalar field, where for every location in, let's say, in configuration space, or for the vehicle, it will really be in position space, where the vehicle, the kinematic state of the vehicle, not velocity, but its position, could include orientation. So for every value of that, you have every position in that space, you have a scalar variable we call a potential, analogous to like electrical potential or potential energy. And that potential will be designed to be a continuous function of the spatial position, so you can compute its gradient. And the notion would be you go downhill in that potential. So you have some algorithm for how to go downhill, and that algorithm can amount to a dynamic system. For instance, if it's really the gradient, you compute the derivative in space, and then you say your rate of change is corresponding to the gradient. So if it's very steep, you go fast, and the direction is really the gradient, so the direction of steepest descent, then that is really a dynamic system. I'll show something about that in a moment. And so that potential is then designed to express the task constraint. So the notion would be that if you have obstacles as hills, so you build some increase in potential for the obstacles, and you have targets as valleys, so the minimum is the target, and there's a valley leading to the target, then going downhill will take you to the target. And because you never go uphill, so you will not run into obstacles if you're not already in one initially, right? And so it's a very intuitive heuristic notion. Here's an example of a potential that's constructed that way, and there was a kind of some methodology of how to best design these. The obstacle contributions would often be range limited because you might not even have sensory information about an obstacle until you're close enough. That's an issue when you use it with real data. The somewhat abrupt way this comes up. And you want to make sure that the potential arises before you collide with the obstacle, right? So it's outside of this hill. So inside of this little hill would be then the obstacle. Yeah, here's an example from that chapter. It's a more realistic example where you would have these obstacle contributions, would be little hills, that are have a gradient, and then the target component would be a potential that has a minimum at the target. It would be typically very broad because you want to have some gradient toward the target everywhere. And if you're using the gradient, when you do grade descent, then the steepest direction will be dominated by steeper contributions. So if the obstacles are steep like this, then if you sum them up, they will dominate when you're close to these obstacles. So you will be primarily doing obstacle avoidance. And when you're far enough from the obstacles, then the target will have a strong influence. So somewhat analogous to the attractor dynamics approach, right? Where the steepness of the, that's the zero crossing, it's not the minimum, right? And you will have an opportunity to think about what the difference is between these two. That's very intrusive, and that's one of the attractions of that. So the space over which this takes place, I already give you part of the answer that you'll have to find out. That's the configuration space or your kinematic space. It's the positional. If you are at the target, you are in a particular location. Remember, in the attractor dynamics, it's a velocity kind of space. When you're in the attractor, you're moving. It's a heading direction. So it's, in that sense, it's very different how it maps, but it's also dynamically assisted. You already saw this in this book, in the article that some of you read for the exercise we'll discuss today, right? They did some of this work. Yeah, it is a heuristic approach. It doesn't guarantee that it finds a path when there is one. It's actually, it can be used local or global. So there are versions where it uses a map to do this, and it can be based on sensory information. So then it's local. And I will actually go a little bit into that in a moment when you use it locally. Here's an example, a famous, often referred to example of this context called chicken cage, where you would be attracted into this obstacle configuration because the target is behind it. And then you might get stuck here, and I'll say exactly in which sense. Or this could be an example where you might have a collision that is, there's a arrow pointing to, you're familiar with the configuration from the attractor dynamics approach, right? And there could be situations where the repulsion here, this vector is the repulsion from this obstacle, this vector is the repulsion from that obstacle, this is the attraction. If you don't do that right, then you would press through, even though you might potentially collide. And for instance, this is an issue of, do you take into account the vehicle size? And it's not contained in the original approach. It's a heuristic thing of then having some ad hoc criteria for how to deal with that. For instance, adding to the obstacles something about vehicle size. This, again, this approach was developed for arms originally, and it can be done in configuration space. So this is some academic example of 2D robot arm. This is a complicated chain, kinematic chain, this little squiggle there, and that chain can then wiggle through an opening to reach a target, right? Even we humans would have a difficulty maybe if we have to insert our arm into something, and about obstacle, we would probably not do it collision free, which is actually sort of do it with haptics. So that fact that it scales like that made it also attractive. Now, I should perhaps say that initially when Kati developed that, it really played on properties of robot arms. And I'll come back to that a little bit in the second part of the course when we talk about arm kinematics. And there were essentially this notion that you can tie the dynamics of the arm, right? When arms move, they have inertial coupling and interaction torque and things like that, that you can tie that to this approach, and that you can express constraints about the dynamics of the arm in these terms. this was not realized in practice for many decades, even though now there are, and for practical computational reasons, I mentioned that in the ARM section, because real-time computing of these things used to be difficult. And now there are some approaches that really leverage that part. So this is something where the planning is tied to the control, and we'll talk about that in the second part, of course. So here's just purely kinematic. Yeah, so this paper that you read, the Feijin, I think Feijin was the first author, Warren paper, studied this a little bit and compared it to the attractor dynamics approach in a sense, just numerically or sort of experimentally, right? And they did that because they were trying to fit the human data and essentially asking themselves which of these approaches works better. I had taught them the attractor dynamics approach. It wasn't so mainstream at the time, and they had someone in the team from the MIT actually who had learned about the potential field approach, I guess, from actually one of the co-authors was someone in that field who knows this, and so they compared it, the new approach to the established approach. That's the motivation for that. And so I want to highlight a few things about that. You might have read that. So here's an example where there are these obstacles that are modeled here as cylinders. So the width of the cylinder reflects the obstacle size, and this is just could be a point-like obstacle, but you add a area around it so that your vehicle, given its width, will avoid it, and you kind of a safety margin. Just add something to it, and you have a goal. And this is an example. The attractor dynamics approach would maybe have gone through this way very smoothly, and the obstacle, the potential field approach would have done this very wiggly path. You can see that it needs to run into this boundary where the obstacle contribution begins to even begin to take into account the obstacle. And once it's inside, then it will turn somewhat sharply as the gradient pushes it down and then go outside. And as it goes outside this obstacle, it doesn't really take the goal very much into account. That's why it turns so sharply. And then it enters the next obstacle, and so it goes against the grain. So this intuitively, this is not very, very good as a path. And it also gets even closer to the obstacle than the attractor dynamic approach. And that's sort of intuitively why they say it's not as good in this case. But you have to analyze this a little bit more carefully. One can, they distinguish different cases actually in their paper. So it has to do with how sharp the distance dependence of the potential is compared to the distance dependence of the terms in the attractor dynamics approach, right? In the attractor dynamics approach, the distance dependence reflects ultimately also sensor properties, over which distance can you actually sense something. It has to be smaller than the largest distance. You can only avoid an obstacle that you sense. Right? And then you can use this exponential scaling, for instance, to give it a unique scale. And so if you're very short-sighted, then the attractor dynamics approach would also do very abrupt things, right? It's not a good model of the humans because the humans do see the obstacles all along. For the potential field, it's not as easy because if you make the obstacles very smooth, rising smoothly, then this balance of obstacle versus to target acquisition isn't right, and you're too influenced by the target. And if you make it very sharp, this sort of stuff happens. And so, roughly speaking, when this is the case, that is that the potential is sharper in space than this distance dependence of the repulsion term in the attractor dynamics approach, then you get that the attractor dynamics approach makes a smooth trajectory and the potential field makes these very abrupt trajectories. It's very intuitive that there's steep things and you run into that, and now you're going to be totally determined. By the obstacle, the only thing you do is get away from it, orthogonal away from it. And so you don't take into account that you're actually heading somewhere. So they elaborated that a little bit. And they also then pinpointed the different ways these approaches fail. So the heuristic approaches, they always work correctly, and they fail in slightly different ways. So here is an example of the potential field approach ending up here in this situation. It's called the spurious attractor. So these are obstacle locations around which, they erect these potentials, single points around which they make these repulsive force nets. Here's the goal. So the agent is sort of pushed into the obstacles by heading to the goal. And the potential field approach sort of generically has a failure possibility that's called spurious attractor in the sense, it's called local minimum, I think. It's this, not sure. So I think it's called local minimum. Exactly. Spurious attractor is our attractor dynamics failure. This is called the problem of local minimum. And in a way, it's very generic, can maybe form an intuition for that. If you have a wide valley, right? You're walking in the Alps down valleys. It would be broad and wide because the attraction to the target should be global. And then you put up little hills there. And you can imagine that for many of these little hills, before the hill, there would be a little mountain leg. If you think of the mountains. And in this broad valley, if you bring it up, then there will be two competing influences on the gradient, and the gradient will change sign. And that's how a little valley like that forms. So that will be a minimum, which isn't where you want to be. It's not the minimum at the target, it's some other minimum. And so in a sense, it's generic. There is even some mathematical analysis of how commonly it occurs. And so it occurs quite common. It's very intuitive for us. You get it all the time. So as long as the obstacle is in front of the target, there's a tendency for these things to form. And so people who built these potential field approaches for vehicles as a reactive thing encounter it all the time, and they have some workarounds. So there are workarounds essentially noticing that there is such a thing. This can happen by just tracking your movements and seeing that you're stuck, and then doing something like adding another contribution or giving you a random vector to get out of the local minimum, right? Sort of like in numerical algorithms who have problems like that for optimization. And so there are pragmatic solutions to that, not very elegant. The attractor dynamics approach can have a problem in a similar situation. So here's an example of this working correctly, the other one, but there is an example here where the attractor dynamics approach generates a path between two obstacles, and this would be conditions where, according to the formulas, the vehicle is too wide. It shouldn't pass through these two obstacles. It would collide with some of these obstacles. This is actually something that we described in our original paper. I'll come back to that. We described that in the paper in 92, Michael Dose and myself, because we did notice that. The intuitive sense for that is that, remember these repulsive forcelets, right? If I have an obstacle somewhere here, there will be a repeller here, so it pushes me away on this side. That's it. There's also the other path, but that's the other one here, right? Then I'm fine. But if I'm on the inner side of that obstacle, like this obstacle here, either could go this way or this obstacle pushes me inwards. And when it does that, now there's sort of an attraction there. And then I have an obstacle on the other side, like out here, that also has a condition where it pushes me toward this left side. And so that could make an attractor, right? There could be sort of a emergent attractor. We talked about that. And that would be fine if I can really pass through this, but it might not be right. And the most extreme example that we discussed in the Dose and Schöner paper is if you have really samples, these obstacles are just measurements, and you have a lot of measurements here, and for each one you erect a repeller, so there's a huge force in this direction, and then you also have a lot of measurements here on this side that push you in this direction, and you have just one measurement in the middle that tells you can't pass through here. But there are all these forces pushing in, and then the little one force that's pushing you away will not overcome it. And this is what happens here. This here or that one would, for instance, push you away from this direction. But these contributions on the left and the right, they could overpower that vote, and that leads to the spurious attractor. That's what we call a spurious attractor. It's an attractor where one shouldn't be, where, according to the rules, you should. And so that's a problem of the attractor dynamics approach. It is actually more a problem of the attractor dynamics approach when it is used in the symbolic mode, where you can have these different contributions that you just number and sum. Now, in the example I was telling you, it comes because you have a lot of contributions on the left, a lot on the right, and just one in the middle. If it's sensors, you have equal sensors everywhere, and you can arrange for these sensors to have different weights because you're going to be close to one particular obstacle as you approach, right? Going to be close to one particular obstacle and not to the others at the same time. And so this one will dominate, and then you will be repelled just from this one. So with the sensor-based or sub-symbolic approach, that is exotic for this to happen. It doesn't really happen, even though it's not theoretically guaranteed that it doesn't happen. We proposed actually a solution at the time. The solution was, in a case like this, to just select a few obstacles. In fact, to only select 2 obstacles, the ones with which you're most likely to collide, and let these figure out if you can pass between them or go around. And as you, for instance, if you go around these 2, like here, maybe these 2, and you have to decide to go around these 2, then you would maybe go in this direction, and then it switches, like now these 2 are the most colliding ones, and you would have to go around those, and so on. And that's a way to solve that. So this, in this paper, I didn't give you this paper to read because then we did something fairly complex. I'll come to that. Very complex to also do that with dynamics, and that was like a neurodynamics. Yes.
Is this one a heuristic solution, or does it actually fix the problem?
It's also heuristic because you could, I mean, what you can do is that you can really be collision free. That is, you know, if you always take the 2 obstacles you're closest to, you can always make sure that you don't collide with these 2. And if there's no inertia term, but it's this first order dynamics, not the Warren one, then you know you switch to a new pair, then you know you will avoid collision with that pair. It's still heuristic because it doesn't find a path where there is one, and so it can actually end up the same thing happens, that you can wander around there. We find in practice quite difficult to get that situation. In practice, our approach often finds the way out, but it's actually heuristic. So we actually try to establish that it also has these local minima. It's not minima in our sense, but local, that it gets stuck somewhere, but that is not easy to demonstrate, actually, even though it's theoretically possible. So that's the solution to that. And the autonomous thing would be to not do it with an algorithm, but you know, also do it with dynamic system. That's more our hobby, to think, can I all do it with a dynamic system? So that works, and there could be simpler ways of how to do that. There is also a solution to the potential field approach problem of local minima that is exact. And that's called sometimes navigation function approach, was developed by someone working with Kodychek, Hilman and Kodychek. They called it navigation function. That is, that's a case where they compute the potential. Now, so in the attractor dynamics approach and in the mainstream potential field approach, you just assemble the potential, or in our case, the dynamics, by adding terms, right? We just added the obstacle avoidance target term, and they just add these different potentials. And so the function that emerges is just a question of the terms that you add. But what you could also do is you could say, I will create a potential that has the right maxima and the right minima, where there are no spurious minima that I don't want, right? So I compute that. Actually, one thing that was done early on was to do this ad hoc with the equation, just blanking on the name of that equation. Just very classical equation, this name I just forgot. So it's the equation that describes the electrical potential when you have charges, and the electrostatic potential you can compute from those charges, you know, using Coulomb's law, and that is a electrical potential that has maxima where there are positive charges and minima where there are negative charges. Right? You can figure that out. And again, if I would remember that question of physics, but Maybe you wouldn't know it anyway. So it's like the static case of the Maxwell equation. And so then they are able to show that this only has the minima and the maxima that you're postulating. It doesn't have any other things. The problem with that, of course, is it is actually kind of complicated to solve that equation, right? It's a partial differential equation. So if this sensor information is updated, you have new information, you have to recompute that every time. That turns out to be quite difficult. It's a nice theoretical solution, but to my knowledge, has never been used in practice, except in the original paper with some, I think it was simulation. So it is a somewhat academic solution to that, right? And the practical thing is what I hinted at, that you have ad hoc algorithms that detect that you're in the minimum, then change a little bit the terms or add some perturbation to get out of the minimum. But that's the spirit of this low-level approach, right? To do that style. Good. So one can actually characterize quite conceptually what the difference is between the attractor dynamics and potential body. Not in performance as it does in this paper, but conceptually, how do they relate? And I wanted to invite you to do this in this exercise, to write a little bit about that. And then we discuss it. I think next week we try to discuss it, and then it gives you a wider perspective. This actually is something that shows up again in the robotics of arms. I already gave part of the answer, but you can go deep into that. This is something that I did 2 years ago as an essay. People were to write about this. This is when they gave me ChatGPT answers. Some people, 5 people. And that was kind of interesting experience. It was the first time I had this problem in this course. And this is when I decided to no longer give bonus points because I didn't want to have to deal with such things. And it's interesting in 2 ways. I mean, first of all, I say this just for once. I said that in the introduction, right? We can have all kinds of ideas of whether AI tools like ChatGPT are useful or not. But when you learn to write and you use ChatGPT, then you don't learn to write, right? So for you to learn something, you have to not use these tools, right? So this is not this academic issue, should I never use this? Maybe you can use it at some point, but if you need to acquire the skill to write, and you need to acquire the skill to write even just to be able to check text that ChatGPT did. Very similar for coding, right? If you can make AI tools that can help you code, but if you're trying to learn to code, then you can't use these tools because then you don't learn to code. Just learn to use these tools. And in fact, in coding, everyone knows that these automatic AI coding tools make a lot of mistakes, and that you have to, as a programmer, you can figure out these mistakes, but only if you know how to program, right? So you have to learn to code in order to use these tools, right? And this is sort of a very clear issue. There is no question about the role of AI tools in education. They should not be used unless the goal is to learn how to use them. But in all other cases, you can't use them because you have to learn the skill so that later you can use them, right? Maybe if that's what you want. And so that's sort of just my preaching about the attitude. Sometimes there's some atmosphere that we have to figure out, we don't know. No, it's very clear. I mean, for educational purposes, it's very clear what the policy should be. No, people say it's like pocket calculator. Yeah, you don't have to do arithmetic, mental arithmetic, or written arithmetic in practice. When the goal is to learn mental arithmetic, then you can use a pocket calculator because then you won't learn mental arithmetic. Some mental arithmetic is actually really needed. If you do analytical computations where you have to solve equations like we just did, you sometimes have to know how to compute the exponent of something, and it would be very impractical to go to a pocket calculator to find out that x to the power of 5 times x to the power of 7 is x to the power of 12, right? And that little arithmetic of adding the exponents would be not something that you want to delegate to a pocket calculator. So, even there is the same analogy, even though we think of this as more trivial. The other thing that was interesting was that ChatGPT gave reasonable sounding text, and we saw immediately the text was artificial, way too good, the English, way too structured. And that is just sort of surprising because the attractor dynamic approach, there may be 20 papers about it or 30. The potential field approach, maybe there are more papers about it, but it did say things that are true about both of these approaches. And that shows, how much, because this is really just a way to search in the literature. And of course, scientific papers are very present in these data sets because they're all free, open in the internet. And so it's very good at faking scientific texts. That's why it's so seductive to use as students. And then the interesting thing is when you look a bit more closely. So first, it seems like this is a good solution because it does really talk about these two approaches appropriately. But then when you look more closely, then you saw that they didn't get it at all because the difference between these two approaches, because in both cases you talk about attraction and repulsion, right? You're repelled from the potential, and you're repelled, in the attractor approach, you're also a repeller, and you're attracted to the target, and you're attracted. And the conceptual resolution wasn't fine enough for it to show that it's two different things. So this is like my pointer to you. You really have to think about what you're attracted from or to, and what you're repelled from, right? And then you have the answer to that exercise. And ChatGPT was not able to do that because it doesn't actually know what it's talking about, right? It's just making word salads that matches the style of the material that it has. And so for it, attraction is attraction. It will use attraction wherever it can use attraction, or where other texts also use attraction. And that this attraction refers to something that will not be clear from the context. Good. So that's a little parenthesis about that. And then we'll have a little conversation about that next week. And not about the AI stuff, but about what this meaning is. This is, yeah. No. Okay. Good. Yeah, so far. Now I wanted to say a little bit more about the potential field approach as a reactive planner. So when it's not driven by discrete different contributions, but really from sensor information, somewhat like the low-level or subsymbolic attractor dynamics approach. That's actually the approach that is most commonly now, or the way the potential field approach is most commonly used now. And it's sort of part of behavior-based robotics that I wanted to expand a little bit on this. This is just Arkin is sort of the person who pushed that ahead. It's also a long time ago, but there's more recent work that does that quite well. So I showed that before. It's just this little corner. So you have all this stuff here, which might have here really a deliberate planner of the way we just talked about. And then when you get to actually running the robot, then you have a little reactive planner schema controller. That's what I'll show you. That's a behavior-based potential field approach. And there are, strategic planning things and user interface and all kinds of things. This is from an Arkin paper. So here's an example of an architecture in this behavior-based style. They talk about schema. It should be schemata, but then Americans, they just say schemas when it's more than one. But it's this Latin word that they mean. And it is, in practice, just pieces of code, right? It's just algorithmically done. So the different things they write down here and call schema are just little subroutines that take, called up with certain kinds of sensor information, and then they hand that down to the calling routine. So here, for instance, a particular motor schema would have, for instance, certain perceptual schema. That would mean it gets sensor information, has a little piece of code that extracts from that distance or, some other factor that plays a role. And it has maybe also some schemata that you call the receptor, where they have internal sensors, like this would be the body sensors, kinematic, knowing its own state, kinematic state. And there could be some, this is essentially the computer bus, right? It has, it's a message-based system, so it reflects algorithmic issues that they all listen to all the kind of sensor messages that are, and just the right schema can pull out its message. And this was going to that level of thinking that this was how this was conceived. And then so sensors, internal, external sensors, internal sensors all just contribute to, speak to the schema, little behavior that is sensitive to that, right? So that's this idea of not having a word model, but having specialized sensory channels for every different behavior. And then on the output side, they are just specifying something for the motor systems. The motor system ultimately is a vector, depending, for instance, if it's a vehicle, it might be a vector that is just a velocity vector, or could have some additional degrees of freedom. And every module might only fill some of the entries into that. Like you could have a speed control that only is the length of the velocity vector, and another one could be orientational control and so on. So they don't all have to specify everything, and they would just be added up. Yeah, and to give you a little more concrete sense, here's a list from one of those papers of the kind of schemata. I use schemata here, they say schemas, that they had. Move ahead is very, so target where you know the coordinates in absolute terms, you have a compass, or move to a goal where you're using, have some other information about path following, avoiding a static obstacle. This would be a whole little movement. Dodge would be where to an event you make a whole little movement to avoid something, not just a update of your current heading. And a couple more like that. Probe dock, would be to have a particular orientation in the world and so on. So for each of those, they have a little code that takes a little bit of information and puts out a motor command. And these motor commands are just just added up. And it's the architecture that decides, this is not specified here, but we'll look at that in more detail in a moment, that only one of those motor behaviors might be on, or two might be on at the same time. The priority function would say, if there's an obstacle, if any obstacles behavior gets some input, then that's going to be the module that's active, and everything else is not active. Not active meaning not sending anything here. And that's how you could sort of organize across these different behaviors, or would have flexibility, would not just do averaging all the time. Here, some example of these schemata, for instance, hard to see here, perhaps this is a converging vector field. So this illustrates potential fields. You could also represent, instead of the potential, you just plot the gradient, right? That's a vector field. And then the if converging, I think, is it converging or is it expanding? I can't actually see that, but I think it might be converging. That when we're going to a goal, this would be a road following. There is some vectors that push you onto that plane, so you can follow that. This is a longish obstacle. This is a roundish obstacle. And they have more like that. And this would be an example where when you just add them all up, you see here there is this pushing toward that path, and there's some global vector to the goal, and then there are some local obstacles here. I don't know where it is, actually somewhere here, that make that the path of this thing goes in this funny way. And that's how this would emerge. Right? There will be. So this will be an idea that these different contributions are activated as you go along. Right? Suddenly you see another obstacle, while another contribution comes up, the vectors change a little bit, and therefore you're going a different way. So it feels very much like track dynamics, except that it's that you're not in an attractor, right? You're actually always having these vectors that drive you. That's what you need to think about. You're only in an attractor once you're there. One can actually algorithmically build intelligent looking stuff that way. So it's all locally, always just doing these very simple things. But by coupling these different subroutines in a certain way, sometimes having counters also that keep track of having done things multiple ways. So this is somehow a trash collection device that, when certain conditions are detected, and then does something else. And if not, it's actually, I haven't really found out how it goes away from here to get to any of these ones. This may be incomplete, I don't know, but just to give you an impression, this is of this design whereby saying local things between the different environments and the sensory conditions that activate different routes, you can do something intelligent looking. So it's not really algorithmic in the sense of a of a flow of command, but it is still recalling the different routines and executing what they do, and only when the routine is done will another routine be allowed to act. Yeah, I forgot which paper this is from, and there's lots of stuff like that in literature. It's not so important. I actually want to show this. This is a cool group in Kaiserslautern who have pushed this really quite far. I think they're still doing this now. This is about 10 years or 15 years old. So this is the most systematic view. It's very charming. They have some papers where you can get the map of the algorithm. It's like a huge map of these elementary behaviors, how they're coupled, and you can sort of zoom in. It's like a huge map, and they have some code for how to design that, a graphical compiler for designing the behavior of the robot. So this would be an elementary behavior, and it has sort of two different flow directions. So remember, behavior based, the idea is that you're encapsulating the information, that is, you're not sharing information. It's just sort of like encapsulated coding, right? That you're not sharing just broadly. The world model will be something, every behavior can take something from the world model, right? And this is one of the bad things, that it would have all kinds of consequences when you change something in the world model. And here, every behavior has its own sensory channel. So there is some input, and the module, the behavior is designed so that with that input, it does the right thing, whatever this encodes. And the only way that you allow is for that module to be active or not active. So you can activate it and you can deactivate it. And so on the computer, it really means you call that routine or you don't. And you can also have, you can have multiple inputs like that, but you can also have, so multiple things can activate it, and you can have some kind of logic that you need 3 votes to get activated. And also it can activate or deactivate someone else, right? Some other behavior. And that is just free of information, just activates or not. Doesn't give particular information. Different behaviors can be coupled in terms of the information they have, however, because the output of one of those might be input to another one. But that is really, by design, there is, because you characterize what kind of information that is, and then the output has to be a legitimate input to another behavior. That is, if as the output of this you get a distance, and some other module has that as an input, then they can be chained that way. This is what was called originally by Rodney Brooks subsumption, that a module can get its input directly from sensor or from some other function that provides that same kind of output. That's how you could make more complex architectures where there's some sensory flow. But that will be very rigid. That is, you're not allowing just anyone to hand the sensory information to just anyone else. It's always this kind of information, this category, that you have to design what kind of categories of information you have. And it's pre-specified which module can take which kind of information. Yeah, and then they do build architectures that way. I think I don't even want to, here you see the different inputs here. This would be an example where the rotation behavior fuses, so it can have more than one source of that. This might vote for a certain rotation, and the object orientation might, orienting to an object might propose a certain orientation, and this module would have some rule that's built into it, fixed, of how it does that. It would be averages down or something like that. And they have designed all kinds of elementary circuits like that do elementary things. So for instance, this would be arbitration, where this decides among 3 inputs which one to give most priority. It has some weighting factors for that. Also transmitted, and see the activation here is also flowing in here. And I could just show something. This is a winner takes all arbitration, for instance, that selects one of those sources and so on. So with these kinds of things, and if you look up their paper, they have a whole list of these. You said in little sub-architectures, and then you can combine these sub-architectures, and you can come up to then have a pretty complex system that behaves, it does it's a sort of fun kind of intelligence that it is not just like a control system. It really makes decisions and can do sequences and select different behaviors triggered by some events and so on. And you can build in even things like that. It would try something and then give up, so that you have like hypothesis testing kind of behavior, having some internal counter that makes that some module deactivates itself after some time and stuff like that. Here's another example. I want to take you through these, how you then combine stuff this way. And they did demonstrate this on vehicles, on it's actually, I think that everything other than the vehicle was actually just simulated. I think they didn't have any manipulation. I don't think I'm not aware of any manipulation they had. Has some user interface stuff also, that this robot could speak and have something where it would make animated face, I don't know why that. So it's a framework that has been scaled to the real world. I don't know if it's really now in deployment anywhere, but that's sort of the furthest this has been kicked. So generally, I would say that after this initial enthusiasm for these behavior-based approaches, the niche that was found was then in these reactive components of systems. And the systems themselves are now really more classical. And of course, they use neural networks there quite a lot, but not in this robotic sense. They would use that to compute some information that is then taken up by the reactive element. So that the scaling of the behavior base to become more and more cognitive, I think that has sort of stalled. And this group has pushed it maybe the furthest it can, which is an interesting issue for us when we're thinking about cognition, right? We have this program in the winter semester. I teach about that program of understanding cognition, also in the, sort of from low-level sensory motor kind of stuff, and how that could leverage up to cognition. And in the brain, of course, it's not subroutines. It's really all little neural networks. We think of them as recount dynamical neural networks, and then there is nothing else. This is really very few people really do that. Most people who use neural networks still have an algorithm that organizes the flow of which network is called when. And so that's a research problem, how to get real human-like cognition out of a system like that. This could be sort of thought of as the robotic analogy to that. And of course, there's no reason why engineers would have to do this in a brain-like way. So they're very happy to do this with an algorithm, and just not care about whether that's not doable in the brain. The only concern when they do this with neural networks is that it's learnable. Learnable really just means that you don't design by hand some of the behaviors or tune them somehow from experience. And that doesn't mix so well with the algorithm. So that's one of the problems. They call that neurosymbolics, right? How to combine these two things. That's for that purpose. It's actually not, it's more, I would call that more a design issue, right? Because it's not really learning from experience. It's actually learning by giving examples to this robot, what kind of situations arise and what it should do. Learning from experience would be a robot that can already behave and then itself finds out when to learn and what was a success and what not. And so it's kind of a different proposition. Also an interesting field, sometimes called continuous learning. Good. Okay. So I'm not going to go much deeper into that. Just to give you a little bit of perspective on that. The Bornstein and Korn is often referred to because it's conceptually very clear. And they developed some filtering techniques that are used in a lot of other approaches now, even though the literal algorithm they developed in the 90s is no longer being used. And I want to show it because of that influence, but also because it has a real analogy to the effective approach, even though it's not technically doing it that way. So this comes out of the sensor of the time, ultrasound lasers, ultrasound devices. This is essentially as a distance sensor, and the ultrasound distance sensor is nice because it has time of flight measurement of distance with the speed of sound, and therefore it's an exact distance measure with some precision, but it's not in principle exact. Compared to the kind of stuff I was showing, right, where you look at the reflected light, which is just heuristically some distance dependent, but it depends on the reflective properties and all kind of things. And now we have, of course, laser rangefinders. This was before laser rangefinders, and those first of all are faster, right? Sound still somewhat slow, and you will see other advantages they have in a moment. So I don't think these ultrasound sensors are really used much anymore, even though there are a lot of academic robots that use them. But I don't think in practice they're used anymore. So they have an interesting problem. It's a practical problem, but it's interesting for to develop new techniques, that the sound is reflected only if you have if the reflected surface is at the correct angle to your beam, right? If you're looking at a sound beam you send out and the angle is this way, you don't get any echo, right? I'm all aware of that, right? The sound is reflected somewhat like a beam, roughly speaking. You know, that's true for the radar as well. Some of you might know that, right? Radar. For instance, ships have this radar tube. So you have a little cube where there are right angles, metallic, reflective surfaces at right angles to each other. And this makes that from any direction you get an echo. This is so that on the radar you see your ship. You don't miss the ship because you really want to avoid collision with ships or track them and so on. And then stealth is the opposite, where you want to not be detected, right? And that's when you make sure that there is only one angle at which you would, like these stealth airplanes, right? You would only get a radar echo if the beam happens to hit it exactly in the right angle, which is very, very unlikely and only briefly true, right? And so those are not very visible. But this is a very general problem, right? You had a question about that?
Yeah. When they choose here.
No, it's not actually a cube. I just couldn't describe it in language enough. So it's this. Let's see here. It would be a. So there's a wall here and another wall like that, and then there would be. And there would be a vertical wall, and you see this here would be like an opening, like it's a cube that's built from the diagonals. You know, it's and so these diagonals are three surfaces that are right angles. So any beam that comes is sort of reflected off the other ones, and in any direction, except if you hit exactly along the line of one of those lines, which is very rare. And so you get very reliable echo from that, right? And that's what every ship you can look at that has that on top of a little cube like that, so that it's very visible on the radar. And stealth is when you just have one surface, so you don't repeat. Yeah, so that's an interesting problem. So generally, they just want a distance measure, and this is an example of this sort of thing. So you send out your sonar signal, and this makes it not so reliable, right? Because you get a signal only if your object provides a nice angle with your source so you can pick it up. And so the notion is you have to make many measurements, and you will build up a map of the world as you go around, as you accumulate measurements like that. And so this is what they developed very, very down to earth at the time. They call that virtual force field or vector, some words for it, histogram method, I don't remember exactly what it's called. And the idea that you build a grid of the world. So as you move, you have to update your position in the grid. It's sort of like mapping, right? You have to know that now the entries from this particular sonar go into a new cell on the grid. And every time you get an echo, so the echo tells you how time of flight, right? How far that is from your current position in the right direction. And every time you get an echo, you add a number here to that grid. That increases, it's a probability that there is something there. And as you drive around, have enough angles, you have a certain probability that you will have hit the wall at the reflective angle. You know, it's not in sound. It doesn't have to be so precise. You get some echo even if it's a little bit off because it spreads a little. And that's how you build a world map over time. I can imagine how that would go. That was one of the, because it's like an early form of SLAM. Right? That's where some of these ideas come from. So I think this might be an example. I can't actually read the slide, but there. Yeah, no, this is actually about what you do then with that. So when you have built this little map of the world, then now in the world, there are some of the pixels where you have a lot of probability there is something there. So you want to avoid that. And the notion that they had is that from the robot's point of view, in every direction, you're going to add up all the pixels that vote against that direction as a bad direction. This is shown up here as the length of these pointers here, and that would be directions that you don't want to go into. So you only want to go into directions where there are very few counts like that. You can also weigh that with how far away those pixels are, and there you have your, the distance dependence of the repulsive force slit, right? That's there. And so in essence, the robot is looking for directions where there is a low count. And it has a target potentially. I don't know where that is. I think this is the forward direction. I don't remember. There's the target up there. And that gives you also a vector. And you want to take a direction with minimum number of counts that lies close to the target. So it's not quite track dynamics. We would say track dynamics, if now you were to erect dynamics of the heading direction, right? And then you go for the local attractor. They did it algorithmically. That is, they chose the direction where these vectors are small and then took the direction that's closest to the target. It's sort of like finding the right attractor in a way. And you can imagine that can jump around. This is not perfect, but it's also low computational costs. And so that is analogous. It's also in velocity space, heading direction space. And so they are always sitting in a minimum of this repulsive vector field, right? While they move. And as they move around, it's different parts of the grid that make these vectors. So things change. And again, you have to understand why that really works. And this works essentially because it reflects the world, like the vectors always reflect the world. So it's sort of conceptually like a dynamic systems approach. And that worked, somewhat. They had a couple of demonstrations from one of their papers. It also has this property of oscillating a little bit in a corridor. It's not a big problem. And I think this I should have shown earlier. This is an example. This is what I originally wanted to show. This is where the counts then start to build up if you actually have objects there. It's more likely you pick them up. And this is the example. They actually did that in their lab, indoors. They had a few things they built up here. This is the vehicle. And it was actually a tri-wheel vehicle. Well, it's a fashion for a while to do that. And after some roaming, it had this kind of histogram where they really built nice entries here of having stuff where it actually is. It's not always precise, but you can see sort of it building that map. And it's based on the robot actually also always updating where it is, right? In this case, it wasn't actually any SLAM, not in the sense of closing the loop or anything like that. It was just as long as the calibration was good enough to do that. But you could see you could expand it that way. Yeah, this is the other example of where you see clearly that you have these minima of these directional counts, and then you're going to choose a minimum, either this one or that one, maybe this one. And then you're just looking where the target is. I think it's here between A and C. So it would be out here that your target lies, that you're going to choose that. I have lots of slides from that, maybe a little bit overkill. And I have some others actually also how they kept track. And this jumps around, and then you can have some policies not to jump too quickly to a new sector and stuff like that, which we don't have to go all into works. Yeah. So this is these methods have been used, and so you find this still much cited work, even though it's not literally being used today. It is also an example, I find that maybe also interesting, that they had a project of rehabilitation kind of work. I mentioned the autonomous wheelchair, right, last time. They had a project that's like 20 years before us. I think it's like maybe 10 years before us. It was in the late 90s, I think. And we did it like 10 years later. No, we were even closer in time. We were actually somewhat closer in time. This is the same time. And so they had a intelligent, what's that called? Blindenstock, like cane for blind people, right? Where you touch your environment. And so they thought we have a little vehicle at the end of that stick that then finds a collision-free path. So the blind person could just follow that vehicle. And we would just use this kind of approach and low-level sense. It was like maybe this large vehicle at the bottom of the cane. Total failure. No one wanted that at all. I mean, it worked, but it violated so many other constraints. And blind people are very good with these sticks, and they use it as a haptic device, right? They detect the environment, and they get a lot of information out of that. And it's very fast. It's active. They actively move it around. It's not to find just free space. There's a lot more, and people just never really want to use that at all. I find it interesting as a example how you come from engineering solution and try to impose something that's not a good idea. Yeah, our wheelchair, actually worked in that sense that people liked it, but it had problems of economic feasibility. Good. So I'm just listing these different approaches, right? It's a bit boring, but maybe just give you a flavor. Again, around the same time, right? We published ours in 92, this 96, so it's old. Yeah, and kind of interesting that this vehicle stuff was done at the time, and that's why there's academic literature. And now you have autonomous driving vehicles, right? But I wouldn't teach about that because those are just huge kludges of software, and the methods in there are from that literature. And it's like deep learning, right? The theory for that is 30 years old. And now it's just huge code and huge data sets, and there's some tricks of how to do it optimally. But there isn't really much new theory in there. And it's very analogous here, right? The autonomous cars combine all kinds of things, but the ideas are really the ideas, some of the ideas I mentioned. Of course, there's more in those vehicles now than I mentioned. So this is also an approach that is still inside some of the algorithms, maybe tuned to other things, called dynamic windows approach, which is essentially a dynamic variant of the potential field approach. So it's actually interesting with respect to this comparison, check dynamics and potential field, because it goes to the velocity. My answer is going to the velocity level. It does it in somewhat odd ways. So the analogy is not totally direct, but there is some analogy. The goal of this was to make these robots move a little swiftly, fast. And that's why it was fun. They made a video. It's often you have one cool video and everyone loves that. It's still being low level, still using low level sensor information. It wasn't done for anything serious. It was actually for a museum robot that just wandered around a museum. In fact, the algorithm there is a possibility to put in a target, but most of it is actually that it just avoids obstacles. So the idea is to do everything in velocity space. So in a vehicle, there are two velocities. There is the speed and the turning rate. I think that's not correct. I think the actual velocity is the velocity vector, where you have heading direction and speed, right? And that's what the attractor dynamics approach uses. And this is mixing two velocities. The turning rate is sort of the rate of change of your heading, which is something like acceleration, right? Your heading is part of the velocity vector. And now you're looking at how the velocity vector changes. So that's part of acceleration. And the speed is part of velocity. So it's somewhat talking. That's how this algorithmic stuff works. And And so the notion was that you make a new state space that has the rotational velocity that is in degrees here, plus minus 90, and the speed, which is here the long axis, which has some linear scale, so some top velocity can go faster than that. And then you use this configuration space approach idea, that is, you translate any distance sensing you have, like here from the walls and so on, into ultimately into a polygon in the space. And the idea is that you do that by computing. So the boundary you define here is the speeds that you could, so you have a distance measure in certain directions, right? And you're computing the velocities at which that you could currently have, so that you could still stop before you hit that obstacle. And so you have to have some model of that. So it's like a model how good, well, you can brake. So it's an ad hoc model. We have a lookup table where, with this speed, that distance, I can stop, in front of me. What is my demonstrate? What is the distance I need to brake? So based on that, you can compute this configuration space representation in velocity space. And there's some ways of doing that. And the critical idea is that you actually, in the end, only evaluate that within a window of your current speeds. So to do this fast, you're not actually considering the entire map. You're only looking at its local window. And there are some other ways to do. You have a model for how you move piecewise circular. So a constant turning rate and a constant speed give you a piecewise circular trajectory. So that's not important. Yeah, and then you can now, so now you have to select your speed within this window for the next time step, right? It's also implicitly dynamic, that is update that constantly. And the notion is that you have a potential function that where you have different things adding into that, an objective function in your, I think it maximizes that. Just in the sign is arbitrary. It could do potential fit, you can do it also, flip it upside down, go to the maximum. And here you go to the maximum of this function, and that function has different contributions that can express the constraint. Sorry. For instance, it has a constraint of going to the target, a constraint of keeping clear of obstacles, and a constraint of going as fast as you can. And then you design functions that do that, and this is heuristic, where you now, given certain information in the world, you say how much gain do you get from which value of velocity, rotational velocity, and target velocity. And you come up with funny functions like that. If you know the target heading distance, you somehow design a function where the maximum is somewhere, in a good direction, a good turning rate for a good forward speed. This is a function that will change every moment in time when you're running, right? Because all these parameters change. And so there's a computation problem of making fast enough iterations so you can always get good maximum. This is an example of the distance term. So large velocities are not so good, because then you might not be able to brake, and shorter distances are good. And then this pushes you to move fast. So if you only did obstacles, you would, of course, always go slow. And so you want to do something to force you to go fast. And then it's just heuristic. You add this, actually, they smooth, you see these individual contributions because they're based on sort of logical conditions. They're abrupt, right? Because up to here you can move, and then you cannot. Next step. And then they just smooth it with some filters to make it so you can make a gradient ascent here, right? You can find the local maximum going uphill to smooth it. Very ad hoc. And it just works. I mean, I don't need to go into the details. It just works. And so they actually did it. Yes.
On the graphs which you showed for the 3D system, what's the Z scale? Like the evaluation function, what does it allow you to?
What's the vertical?
Yeah.
So that is something like that potential. So it's just some cost function, arbitrary units. So you have different contributions here, some cost function where you have 3 contributions to that cost function, and you're going to maximize the total cost, or I don't know what they call this. Maybe cost, we usually would think of minima, and here, just a gain function, let's say. And so you're looking for the maximum of that to select the correct value. So you're choosing as the next linear and angular velocity, those values that are giving you the maximum for that. And you can, by having a parameter in front of each, you can sort of weigh differently. Like, we would say the observable term has to have priorities and make this better, larger, or make just sure that the units of this are large and that this one maybe is smaller and so on. So in that sense, an arbitrary dimension that just helps you compare the different contributions, and within every contribution, you're maximizing something. Yeah, so this is an example of this working. So they actually had, this is this robot where they use sonar to get the distances, so it's also not very reliable. And the target, I think, was also dead reckoning. This is a system that keeps tracking where it is and just knew where it wanted to be. So here, it's like the demo I showed on the attractor dynamics approach, right? Where the target is somewhere on the other side of the wall, and the vehicle runs along the wall, always repelled by the wall, until it finds the opening and goes in. That's sort of the same idea. It doesn't have to be very precise with the target. And this works, and this is sort of a demo. So you could see this different runs where on one run, it actually did go through the opening. And you can see if it's going too fast. I think here this one is it's just going too fast, then it doesn't have time to turn. So it misses the opening, because within that window that there is no way of how it can do that. The solid line is also, it's going not as fast, but I think there's something about its turning rate is slower, so it can't make the turn. I don't remember exactly what quantities qualified it. So the parameters have to be right for it to be able to turn in time and do that. So the main cool thing about that, it was really moving relatively fast. Yes.
Size of the box where decisions are made to determine, because if that would be larger, then it still could have made it.
Yes, and then it's also ad hoc, and one of the constraints is to do the computation. I mean, first of all, you have to have the sensory data and to the computation. So a small window is also makes the optimization. They do in real-time optimization, makes that more feasible. They do it by gradient ascent, right? So it's not a global optimization. You can go to a local maximum. It's sort of already sitting somewhere, and then as the window moves, the functions will update it. You don't have to compute the whole function, just compute around where you are and then go up, iterate uphill. That's how it works in practice. It's really all very ad hoc. And that's very much the spirit of a lot of this work. And inside your complicated modern algorithms, there are a lot of things like that, also quite ad hoc. That's Tesla is just a huge collection of little tricks like that, right? And it's sort of, it's not just, I don't know that objectively, I don't know what's inside their system. But the impression I mentioned, my work with Volvo, and impression is that to make these systems improve now, you're essentially building a lot of cases, In this case, this is a good approach, then you check that case and you use that, and you have a lot of different solutions for different cases. And that's why it's difficult to publish a paper about how an autonomous car works, because it's a huge kludge of a lot of different partial solutions for partial problems. Yeah, so that's what I would say. So the last thing I wanted to show is this work that was done by Stella Bischenboy from Erlangen, 2 of my former students. These are the 2 guys who married, who were in my lab in Marseille. And they developed this approach. This is sort of the furthest I've seen this pushed. I mentioned, the attractor dynamics approach. I mentioned earlier that there was a group at UPenn who used our approach for collections of robots, right? I didn't talk about this yet, right? I don't think I did. I hope I didn't confuse myself here. So they had looked at collective robotics, and the idea was that you have robots that go to targets, avoid obstacles, but they also have a contribution of how the other robots interact with them. So in that earlier work that was done by At Large, the robots, for instance, might follow each other. So one robot is a target for the other robot, or they might want to keep a certain angle to the other robot, so they move in formation. And that was just sort of an academic exercise. And Stella pushed this to a new level where she asked the robots to collaborate by transporting something jointly. So here is one and the other robot. They have different algorithms. One is called the leader, the other is the helper. And they carry something. This is just a prototype, right? So it's not production. So they carry here the cargo on top. They're going to make some assumptions about that cargo. That is how wide it hangs over the robots at a certain distance, right? So you can see that, right? This is a box that they carry, and they are supposed to not collide with stuff in the environment. And then there will be, they have the same sensors, distance sensors, and all of this is just about that. So they don't have actually sensors about the elevation of obstacles. So there's one level at which they measure everything. All of that would be to be improved in the real world. So here's a little bit inside. So one of these robots, individual robots, has the same structure as the one we discussed. It has 2 active wheels. It has a forward direction, right? In terms of these wheels, it has sensors. I don't know how many distance sensors. It has dead reckoning, so the targets are still given in coordinates. And it also has sensors that sense how the platform on which the cargo lies is oriented relative to the robot. That's really how they know where the other robot is, in which direction the other robot is. The cargo, it's not slipping against the cargo. So the cargo rotates that little platform up there. And so this will be the helper and the leader. And you see now you have additional angles, right? You have the angles to the target, to the obstacle, but you would also have angles that say, how is the cargo oriented relative to my current robot for both? And that's really how they know where the other robot is. Yeah. And so they designed a dynamic system. I can't explain all the details of that, obviously, it's quite complex. So they have to do a couple of other things. So you can certainly see that the helper has to follow the leader. That makes sense, right? The helper also has to avoid obstacles. We typically have the situation like people, some automobile drivers don't sometimes realize when they steer, their body is going to cut off the car, right? It's going to cut corners, and you have to make sure that you don't collide. Like if you have a truck, it's really relevant. I have actually seen people not take that into account and run over the sidewalk. So the helper, the back of the car in a way, has its own sensors and will still avoid obstacles. But you can also have situations where you need to plan to get around. For instance, if the leader comes to an obstacle like that and you want to go here this way, you have to go around it. And you can see that now you have this cutting the corner issue. That is, you have to make sure that it doesn't turn too close so that there's no chance to get the cargo around. And so what they did is they detected situations like that, and all of this is based just on this array of distance information. Now they know where the cargo is, and they have all these distance sensors, and they computed functions that detected situations like that, and then added a term to the equation they call a virtual target. So they put a target up here so that the robot will steer clear of this obstacle. And so that, and then once you're at that target, that term goes off. Now also have a function that controls that, and then it would automatically go around that. So all of this is just done by adding contributions to the dynamics, and the contributions are erected. It's not actually neural activation, it's erected, just there are some computations on the sensor data, and these computations will turn on something or turn off something, depending on the context. I think they had one more thing for the follower, also some virtual targeting. I think it's this situation when, I think this is the front robot, and then if there's a risk that the follower would go too close and then cut through the obstacles, they would also put a virtual target to make it have a wider turn. They would detect that. So this paper contains all these formulas and really quite beautiful, all just simple geometry. And that works just it's amazingly well. This is an example in a simulation where it gets through a rather narrow opening. You can trace, you can really see how the bifurcations happen, right? Here's an example where there is a repeller and two attractors for the leader, and the helper has a single attractor. And then I think in the paper they show that a moment later, there's a bifurcation and the leader goes somewhere else, and then the helper tracks and so on. It's always sitting in the attractor all times. It's really beautiful. So this is an example from the actual demo in the lab. You see this is factory floor. This was this German company, which the name of which I forgot, where they collaborated up in Gimerange. And it's not extraordinarily cluttered. Of course, there is some room, and in factory environments, you don't have that terrible clutter. And again, the sensors are limited to just picking up whatever is on that height where they have the sensors mounted. But they made the demo. They had a national project to fund that, and there was a demo, and they really were able to do that. For instance, if you had a table like that, you might have trouble, right? Because there's only one level where you could get a good signal, like below the table, you're not going to get a distance signal. So there will be some limitations of having simple sensors like that. Yeah, that's all I wanted to say about that. Good. So closing here. So there are quite different approaches. There's a whole spectrum. It's now, I would say, no longer a field that has a lot of theoretical development. It was kind of mature, I would say. So the practice of this field is that people are building these kludges, the practical things they take from this whole repertoire. Yeah, let's just summarize some of them. So these reactive approaches are really the ones that are used all the time. Without the heuristic approaches, you don't really get anything going. But there are deliberate planners and things like that. You might know that the autonomous vehicles that are in actual use are not extremely autonomous. I just saw this in this hospital, Augusta Hospital. They have a level where there are autonomous vehicles driving up and down the corridor to deliver stuff. And it's only autonomous. Well, it's autonomous, but it follows a really pattern. There are markers, and this is all being kept track of. But when you step in front of them, they either stop or they can slightly avoid you in the corridor. It's only this wide. They can avoid you a little bit, but other than that, they would just stop. And they also say, autonomous vehicle, please get out of the way, something like that. Even though they can really stop if you stay there. I wouldn't test that though. And that is means that in practice it's really not in totally difficult environment. It's sort of pre-structured with limited autonomy, but it is ready to be deployed, right? This is as far as it goes, and it's similar for these vacuum cleaners and all of these things. So that is sort of a solved problem. It's more application demand where that's a problem. So autonomous driving out in the street would be perfectly feasible if there were no humans on the road, right? If it was all autonomous vehicles, with heuristics like that, where you allow for every car to stop, maybe also to signal to each other if there's a problem. So it would be doable. It might not be so elegant, but it might be quite doable. But the fact that the streets are not as normed as we think and not simple, just look at the construction sites we have here sometimes, and how the markings are off, and then humans doing all kinds of funny things. That makes a very resilient difficulty, right? But the technology is really roughly there. It's also for driving with humans that we are asking a lot of cognition. That is, we're asking to recognize bicycles and humans, so perceptual things, right? And to even to communicate with humans. Like if you have a pedestrian crossing, then you're looking at the face of the person, or maybe the body configuration, to see, is that person going to cross or not, or is this a child, or things like that, right? And we had a project on intention detection, You can see that that goes much further than just driving a vehicle. That is really a form of artificial intelligence cognition and so on. That's also a bottleneck. When you have this ambition of having vehicles interacting with humans, much more demanding than just vehicle per se. Good.